Hello and welcome. Let's continue with our lecture on general theory of relativity. Today we are speaking about speed of light. In the last lecture, we have seen that as per Maxwell's equation, there is a wave-like propagation of electric and magnetic field, and they are called electromagnetic waves. They propagate at the speed c, which is given by 1 by square root of epsilon and mu naught, which does not depend on the anything other than the property of the medium in which it is propagated. Maxwell also realized that light is an electromagnetic wave and has to propagate at the speed c. Now this deeply impressed Einstein, and he was developing the special theory of relativity. Finally, he made a conclusion. It is in fact the Maxwell's equations which are correct, and it is a Newton's and Galileo's formalism which requires the correction, that is first and second Newton's law. That is where the development of a special theory of relativity happened. Today we will discuss the various aspects of speed of light. It is mainly connecting lecture to justify what are the basic postulates of special theory of relativity, and we also state all these principles and then go ahead with the properly formulating through the mathematics in the coming lectures. Let's briefly cover the history of light starting from Newton to Einstein. As per Newton's, light is made up of small particles called corpuscles moving in straight line with very high speed. And it is literally saying that the velocity of light is infinity. It's not very convincing. Even at that time, it looks like Newton is hardly interested in light and related physics. However, this idea, corpuscular theory of light, did not last very long. Soon, we have had Huygens who came up with the wave theory. Huygens principle is very simple and interesting. As per Huygens, light propagates in a spherical wavefront, and each point of the wavefront further emits light as if it is a point source, and their envelope acts like a wavefront in the next step. So this way we have a complete propagation of light as waves. The important point here is that Huygens' model could clearly explain the physical phenomena such as interference, diffraction very easily. So this made this model very attractive because Newton's theory was in fact did not explain any of these using the corpuscular theory. Now comes Maxwell, who gives the complete description of light using the electromagnetic theory, and that is light propagate as a waves. This is basically is the end of a corpuscular theory of light. In earlier centuries, there were some problem. It is believed that wave propagation requires the medium, and it is believed that there exists a ether which is an eternal and spread all over, and entire universe is floating, or at least earth and solar system is floating in the ether. Think of it, it rather look very foolish, and especially when the Maxwell has explained light as electromagnetic waves, though there were no experiment on electromagnetic waves. Electromagnetic waves were produced later. Hertz was very instrumental in understanding electromagnetic waves, and it is a J.C. Bose who produced first electromagnetic waves in the labs, and of course Marconi, who find it convenient to propagate the idea. As per this model, there exists a medium in which everything is buried, and there was search for ether and its properties. Of course, I am not sure Michelson himself was very much worried about ether. At least he was doing all sorts of measurement connected with the velocity of light. He is said to be pioneer in the measuring the speed of light. All his ambition seems to be measuring speed of light more and more precisely. One of the experiment which we was interested is to measure if there any difference in speed of light when going in different direction. One of the reason for this may be to look at properties of ether, if you believed it, or simply to check whether the propagation of light depends on any direction or the source movement. idea is you have Michelson interferometer. Michelson didn't use laser. Lasers came much later. Michelson used a light which split into two and made an exact arm length. One of the interesting part of Michelson interferometer is that it could be easily rotated because the entire optical bench was floating on the mercury bed. So he could rotate his interferometer as he wanted and measure the speed of light in orthogonal direction. If interferometer is on the surface of Earth, then one direction along relative speed along one arm is different from other would lead to a slightly different path covered by light in these two arms and resulting in the fringe shift. If Earth is rotating, velocity is about 50 meter per second. That could be easily converted into v by c square, or you could measure velocity as we propagate against the ether, that is orbital velocity of Earth around the sun. That would be v by c is about 10 to the power minus 4. Once you have that, then you can find out the fringe shift, that is n is equal to 2l by lambda v square by c square. So this is an expression which would give you shift in the fringe when you rotate or change the direction. The Michelson experiment is popularly known as a null result, as Michelson did not see any change in the speed of light in any direction. That means the speed of light is same in this every direction. That means there is no effect of ether on the propagation of light or the velocity of the Earth on the propagation of light. It is interesting, after formulating a special theory of relativity, Einstein seems to have claimed that he was not aware of the Michelson experiment and did not give any credit to Michelson. However, Michelson is a pioneer on his own way to measure the speed of light, and it doesn't require any big shot to give you some credit. As long as your work is genuine, it would stay on. Historians currently say that Einstein might not have been candid about. So these are the facts. Sometimes, irrespective of great scientists they are also human beings. That is where some of the problems do come. So let's go ahead with postulates of special theory of relativity. Based on all this, it was clear to Einstein that Newtonian mechanics has to be modified, and he formulated a new mechanic which is based on the two fundamental postulates. The postulate, which essentially means that it is a kind of an assumption which acts as a foundation to the theory, and way to test the postulate is either by explicitly showing that the postulate is wrong, or you check the various consequences of theory. The theory make a wrong prediction, then the postulate must be wrong. That is how you say that the speed of light may or may not maximum speed at which communication can be done. The special theory of relativity is based on the two postulates. The law of physics is same in all inertial frame. So this is nothing new. It is basically Galilean principle. Now here comes the second and the most interesting, which is different from the Newtonian mechanics, is the speed of light in the vacuum is the same in all inertial frame irrespective of their relative speed. So this is where the difference comes. We have seen when an inertial frame is moving relative to each other, the law of velocity addition, the light simply do not follow this rule. That means that irrespective of speed of observer, the velocity of light is a c, and that becomes a universal constant. And it also says that the speed of light is a maximum speed at which any signal can be exchanged between the observer. That means that no information can propagate faster than the light. So this is the foundation of special theory of relativity. There are also corollaries state that the light should move in a straight line. Now we have seen that some of the shootout between Sita and Geeta. Let's look at what happens if both of them or one of them acquires the laser gun instead of a normal gun. Velocity of light is independent of emitters or observers' velocity or direction of propagation, and it is a universal constant. According to Newton, speed of light would be given by the velocity addition rule. However, Einstein says that that cannot happen, so it should be same for all observers. And we see that this can happen only if the time is different for the inertial observer. If the time is same, then there is no way we can have the velocity of light to be same to all observer if the time is modified to each of these observers, then the speed can be same for all observers. So this is idea of where the relative time enters into special theory. We have fixed the speed of light and the loss of concept of global time, and the time becomes frame dependent. So this is another important concept here in the Newtonian dynamics. We have time is an absolute quantity, and here instead of a time, it is a speed of light becomes an absolute and universal constant, and time loses its status as an absolute quantity, and it would depend on the observer to observer. And of course one can relate time between the different observers. That is what we study later on. So here velocity of light becomes an important quantity or the physical constant in the physics. Now here comes an interesting factor. We know that it is a distance between 2 points which is very critical in the special theory of relativity. That is all dictates the dynamic. In Einstein's formalism basically included negative sign either between 3 spatial component and time component while measuring the distance between the point compared to the Euclidean distance. However, that was a bit of a cumbersome notation and not very friendly. It is Minkowski who is first developed the idea of space-time, where you can have a real time, not an imaginary time as in the Einstein's formulation, and you can have a distances defined instead of Euclidean distance. You define what you call is a pseudo-Euclidean distance. That is one of either space or time acquires the negative quantity, and that is what we call is a space-time. Now in this notation, any event in an inertial frame is determined by 4 quantity, that is a time and 3 spatial coordinates. So if an event A is given by coordinate t1, x1, y1, z1, and event B is given by t2, x2, y2, z2, and so on. So you have space-time coordinate given by orthogonal system where you have event A and B, and the displacement or distance that is called the space-time interval between the event is given by ds square is equal to c square dt square minus dx square dy square minus dz square. So this represents the space-time separation or interval between the two events in a space-time. You note that c square is multiplied to dt in order to make it a dimension of the space. So this way you measure the distance in the space-time. We have completely changed the idea of space-time. Earlier we were following the exactly Euclidean distance. Now we are using a pseudo-Euclidean distance. One of the differences is that a vector is 0, then its magnitude is also 0 in the Euclidean. Because of this sign difference, that breaks down. Here you can have a vector whose length is 0 even if the vector itself is not 0. So that is physically important, which we call is a null direction. We'll come back to that. Here the intervals are given as a dt is equal to t2 minus t1 and dx is given as a x2 minus x1 and so on. The fact that nothing can move faster than light divides the space-time event into 3 separate types. One is called the time-like, light-like, and the space-like event. You can have space-time interval greater than 0, then you call it time-like event where all the material particle can follow, and then you have light-like where its element ds square is 0, and that is what I was referring to. Even if displacement vector is not 0, the distance between the 2 points can be 0 in the pseudo-Euclidean or a Minkowski space, and the intervals are called the light-like, and the space-like separation is when the ds square is negative. This brings us to another important concept of light cone, and a light cone is always referred to with respect to an observer. All the 3 events are separated, and the null event acts like a boundary between the space-like and the time-like event and forms a cone, and that is what we call is a light cone. Let the event A is equal to t1, x1, y1, z1, and B is equal to T2, X2, Y2, Z2 are the 2 separate events in the space-time. Then the ds square separation is given by ds square C dt square minus dx square dy square dz square. So that is a separation between the 2 events. A time-like separated event, the event A and B are time-like separated if the space-time interval ds square is greater than 0. These are the event which can exchange the signal with the massive particle or light. Then comes the light-like or null event. The two events A and B are null separated or light-like separated if the space-time interval between them ds square is equal to 0. These events can exchange only the propagation of light is represented by the light-like or null events. Now it is also important to see, we say light in a loose sense, we know that it is all particle with the zero mass is represented by ds square. Then we have space-like event A and B, space-like separated if the interval ds square is negative. Event cannot exchange any meaningful signals. Now it is important to note here that I am following a very specific convention here, using a positive sign for time and the negative sign for the space, and that is convention called the plus minus minus minus. The relativists, before they state anything, they have to make their notation clear, and which is called the signature. The signature is given by the sign of the spatial and the time coordinate. In this case, I am using a positive for time and a negative for the space. The definition of space-like, time-like and null would get interchanged if you use the convention minus plus plus. In the minus plus 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 notation, there is a convenience that the spatial coordinate comes with the positive distance, which we are using it as a Euclidean distance. On the other hand, your time-like will have a negative displacement. So it is just a convenience one uses based on their liking or disliking. But however, one has to state their preference in the beginning. Otherwise, this sign would get interchanged and your interpretation would also be changed. The light cone is always drawn with respect to the observer, that is treated as the origin of this coordinate system, who would be present here and now. And then you have a light. In this case, the cone structure comes because the space is treated in 2 dimension and time is 1 dimension. So the 2-dimensional plane is called space. In reality, space is a 3 dimension. You can have this with the 1 dimension for space and 1 dimension for time. That would be easy to draw on 2-dimension cone representation of a special theory of relativity. So we have all the t is greater than 0, that is come as a future, and all t is negative values comes as a past. So the light cone again differentiates the 3 set of event with respect to center or observer O. You have all time-like which are inside the light cone, and then all space-like which are outside the light cone, and you have a light-like which is on the light cone. So that means all the event on the light cone can be communicated by sending light from the observer O. So you also have a future light cone and past light cone, that is, which comes all the light sent from past arriving at the observer O. So all these events inside the light cone are time-like. They all can be accessed by the observer O, either by sending light to them or by sending a massive part. So those can be causally contact with the observer O. Again, you have a future and past. Future is where you can communicate by sending the particle. Past is that if at all past observer, any of them have sent the information which can reach to observer at O. Difference between the future and past light cone. So this is the basic idea of light cone. Basic take back from the formulation of special theory of relativity is the speed of light in vacuum is a universal constant. So it is often convenient to take the universal constant or speed of light to be 1. So often when you do a theoretical calculations, you can set the speed of light to be 1. Speed of light has a dimensions of velocity, that is L by t. Now if that has to take value of unity, then we have to have length and time is measured with the same unit, because that is speed becomes the without any unit. So such unit is used in the general relativity often is at c to 1, and then you have a physical distance and the time is measured with the same. You can use interchangeably to measure distance in time or time in distance. So the way to do it, this defines a new way of measuring. For example, the standard of measurement of distance is used as a meter, and the standard is given in the SI unit as a 1 meter stick kept somewhere in the Paris as a measure of standard. However, currently that standard has changed. Now, since the velocity of light is a universal constant, you can redefine the unit of 1 meter as it is a distance traveled by the light in 1 by c seconds, where c is equal to 299792458 meter per second. How it is done is by measuring distance traveled by the light in a given time unit. You start your clock, send a light beam, it propagates for about t is equal to 3.3356 blah 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 nanosecond, and that would be 1 meter. So this is a new definition of a meter. You might have heard that astrophysicists already measure the distances in time. It is called the light year. Light year is the distance traveled by the light in 1 year. So you can have many light years. You know the distance to sun is actually 8 light seconds, and you can refer all the distance with respect to the time. You can refer to your height in terms of seconds, not in meters. Let me stop here. In the next lecture, we'll continue how to measure the distance using light and a clock in little bit more detail, and also how we can come to the idea of invariance of laws of physics with the speed of light in an inertial frame, and Lorentz transformation should come as an outcome of all these postulates. So we will stop here and continue in the next lecture.